So let's try to constructively describe the algebra of sets on X generated by F. So the assumptions here are what I was writing back here: X any set, F any collection of subsets of X. And the algebra of sets on X that is generated by F is what's defined here. So we start with F, and it might not be an algebra of sets. So we throw in the things, the idea is to grow it as little as possible, throwing in the things that we need in order to make it an algebra of sets on X. So let's throw in the empty set, the entire set X that we started with, and complements. So I guess to make this notation make sense, I should probably put no one does this that I've seen, but probably we should decorate it with X and say that we're talking about the algebra of sets. Here we're talking about the algebra of sets on X that is generated by F, because F could, the data as to what X initially was might not be contained in what F is, right? So here we know what X to add in. So I'm talking about the algebra of sets on X generated by F. Okay, so throw in the empty set, throw in complements. So whatever, after you throw these in, throw in the complements of anything that's in there. And that will give you a new set. Let's call it F1. So F1 will be F unioned with the complements of anything that's in F, unioned also with these added in, with the set containing these. So that's F1. So that's great. Now it's closed under complements, right? But it's not closed under finite union. So remember, we need three things for an algebra of sets. We needed to have these in it. We did that. That was easy. We need to be closed under complements. Now that's achieved. We also needed to be closed under finite unions. Now the problem is, if I just say throw in finite unions here, like just throw in any finite unions of things in F1 and create a new larger set, that's not enough to stop there, because then what I have will no longer necessarily be closed under complements. What's the problem? Is that if I take a finite union of things in here and then take its complement, then that will be a finite intersection of things that are in here, right? So what I'm actually going to do is next throw in finite intersections of things in F1, and that will lead to a set which we can call F2. So F2 is F1 unioned with, well, F2 is just the set of all finite intersections of things in F1, which includes all the things in F1, since the things in F1 are one-fold intersections of things in F1. Okay, and now it's no longer closed under complements, but let's throw away all the finite unions and we'll be able to show that it is closed under complements. So throw in finite unions of things in F2, which is the set of finite intersections, and that will give us a new set, F3. And then our claim is that F3 is the algebra of sets on X generated by F. So that is a pretty constructive description, right? You start with F, and then you build this set out of F. The set of finite unions, of finite intersections, of things in F and their complements, and also the empty set and the whole thing. So you can describe exactly what are the elements of this thing. So let's look into proving this claim. First of all, there should be no doubt at all that this is at least a subset. That much is easy. That's because if you have any algebra of sets on X that contains F, then it must be closed under finite unions, finite intersections, complements, and it must contain these things. So let me put it this way. F is definitely a subset of this, right? Because this is defined to be the smallest algebra of sets on X that contains F as a subset. So F is a subset of this. So is F1 then, because F1 consists of complements of things that we already know are in here, and this is closed under complements. So is F2 then, because that consists of finite intersections of things that are in F1 and therefore in here, and we know this thing is closed under finite intersections. And then so is F3, because this thing is closed under finite unions. So this much is easy. It's the other inclusion that we really need to think about. So we know that by throwing all this stuff in, we have collected things that must be in the algebra of sets on X generated by F. The question is, have we gotten all of them, or are there more? Well, this is the smallest algebra of sets on X generated by F. That's what it's defined to be, right? So if we can prove that that F3, where we ended up here, is an algebra of sets on X generated, is an algebra of sets on X that contains F. If we can prove that it is one, then we will have the other inclusion. Then it must contain as a subset the so-called smallest one. So if it is one, then it contains the smallest one. That's what smallest means. So to prove that we have gotten everything, what we have to prove is that what we end up with here, finite unions of finite intersections of complements of things in there, is really an algebra of sets on X that contains F. Okay, contains F, that's easy, because we started with F and then we just built up from there, right? So all that's left is this an algebra of sets on X? So what do we need to check? Here's the definition before I added the blue stuff for sigma algebra. We need to check that the empty set is in there. Okay, check. We threw that in at stage 1, right? We need to check that it's closed under finite union. The blue stuff was for sigma algebras, forget about that. We need to check that it's closed under finite union. And duh, it's closed under finite union because it's the collection of finite unions of things in F2, right? And if you take a finite union, finite unions of things, then that's another finite union of things from F2. So super easy, this is all super easy. And then closed under complements, that's going to take a little bit of effort. So yeah, sure, we made F1 closed under complements, but once we built up to F2 and then to F3, is it still closed under complements? Now there's a lot more stuff to take the complement of. So here's our question the remaining question is F3 closed under complements? Is a collection of finite unions closed under complements? So let A be in F3. And let's take the complement of A. But first let's break down what being in F3 means. It means you're a finite union of things in F2. So say A is, let's call it A1 union A2 union AN. Sometimes when I have a finite union, I like to write it out as a list here rather than with big cup, just to have the psychological feeling that it's finite. It feels more finite when it ends on the page. Okay, so say we have that where A1 through AN are in F2. Now what does it mean for these to be in F2? To be in F2 is to be a finite intersection of things in F1. So each AI, let's call it, can be written as an intersection. Let's say B1, B2, or well, we're going to need some better notation. So AI will be BI1 intersect BI2, and so on, until we reach BI. And then how many of them are there? Well, there could be any number. Let's say it's M of them. And for the ith one, there's M sub I of them. So you could have different numbers of them that each one is an intersection of. Then let's take the complement of A. So the complement of A is the complement of a union. Now let me go ahead and do this instead of writing dot dot dots nested. That's no fun. Let me use I from 1 to n of AI, right? But AI is, what I'm about to write down is an intersection. Let's say from j equals 1 to m sub I of bij. So this is a way of writing this, which is a way of writing AI. Now, De Morgan's law, twice. So the complement operation distributes into here, and the big cup turns into a big cap. And then it distributes into there, and the big cap turns into a big cup. And now we're taking complements of these individual bij's. And you know, the individual bij's are coming from, the individual bij's are coming from F1, which is itself closed under complements, right? Because it contains a bunch of stuff and the complements of all that stuff. So F1 is closed under complements. So these are definitely all in F1. And therefore they're all in F2, right? And so this thing is a union of things in F2. So it is in F3. F3 is the set of finite unions of things in F2. And so see what we've got? We've got a finite intersection of things that are in F3. Now we know that if you're going to have an algebra, forget the blue stuff here, if you're going to have an algebra, then while the definition, our nice tight definition, only explicitly requires closure under finite union and complement, it does also imply that you have closure under finite intersection, right? So if F3 is to be an algebra, then even though we don't need to explicitly prove it, it is true that it is going to end up being closed under finite intersection. What we're seeing here is that if we prove F3 is closed under finite intersection, then we will be done proving that it's closed under complement. This is part of a more general principle, but that's fine to see it in this specific instance. So we're trying to show that this is an F3, right? And we show that this is a finite intersection of things in F3. So we will be done if we can show that F3 is closed under finite intersection, which is something that has to be true anyway if F3 is going to be an algebra of sets on X. Now, let's begin this task. So it is sufficient to show that it's closed under binary intersection. So, meaning intersection of two things. That's thanks to induction. So let's let A and B now reset variable names. No more of the A's and B's up there. So this is a new proof that F3 is closed under finite intersection. Let A and B be elements of F3. Say A. Actually, I really dislike this notation. Let me call them A1 and A2 with the index up there. Since I don't want there to be a mismatch between the role that the B's were playing up here. Even if I say we're resetting notation, it'll still be stuck in my head. Let's say A1 is A1, 1 union A1, 2, etc. So being in F3 means it's a finite union of things from F2, right? Let's say up to n. And A2, let's say this one goes up to m. Where all of these are, all these individual sets here are elements of F2. let's take the intersection of these two. So A1 intersect A2 is an intersection of two finite unions. So one of them is, let's say, from I equals 1 to n, and the other one is from, let's use a different index, j equals 1 to m. And here I'm just writing in a different form this union and this union. This is A1 I, A2 I. So I'm intersecting two things in F3, and I'm hoping that I get something in F3. So I'm hoping I can rewrite this as a finite union of things in F2. Now, from set theory, intersections distribute over unions, and unions distribute over intersections. So, so here, so the way I like to think about it when I'm doing this kind of set algebra is I like to think about when one thing is coming in and intersecting with a union of a bunch of things, then I think about the intersection as though it's a multiplication, and the union as though it's the addition. But it also works the other way around, interestingly. If one thing is coming in and unioning with an intersection of a bunch of things, then I think of the union as a multiplication and the intersections as all being like addition. So I like to think of it that way because my brain is used to applying distributive laws for addition and multiplication. So if you think of this as though it's multiplication and these as though they're sums, then how would you multiply two sums? You would get a double sum, right? It's the same algebraic rule. So from I equals 1, j equals 1 to n, m. So this is a sum of a union of n times m different things. Each one of these things is a product or intersection of this is a mistake. This is a typo. Just like that. And look at this. This is in F2, right? This is in F2 because F2 is the set of finite intersections of things in F1. And a finite intersection of finite intersections is a finite intersection, right? So if you intersect two things in F2, you get something in F2. So this is in F2 because these individual things are in F2. This is in F2 for all I and j. So I'm unioning n times m things in F2. So this is a finite union, although it's a much larger union than these original unions here, union of n things, union of n things. This is a much larger union, but it is a finite union of things in F2. And so we have shown that this is in F3, the set of finite unions of things in F2. All right, so F3 is closed under binary and therefore by induction finite intersections. Therefore, it is closed under complements, since complements can be reframed as finite intersections. And so F3 is an algebra of sets on X. And so it contains the smallest algebra of sets on X. And so we have both inclusions here. And we have, by carrying out this procedure, we have a very constructive way to describe what are the elements of the algebra of sets on X generated by F. So think of this as comparable to the situation in linear algebra where you maybe originally define the subspace of a vector space generated by a set as the smallest subspace that contains that set, which is kind of abstract. This is kind of like describing all the elements. They are all the linear combinations that you can form. So the span of a set of vectors, the smallest subspace containing those vectors, is a set of all linear combinations that you can form out of the things in the generating set. Here, instead of taking linear combinations of things in the generating set, in this context, we take a different kind of combinations. Intersection-y and union-y combinations of things. Okay, so the next question then is, now that we have a constructive description for this thing, what about this thing? Sigma algebra of sets on X. It's not so different of a concept, it's just that we're interested in sets that are closed under countable unions rather than just finite. So it sounds like we just need to do a little bit more than just these steps. Maybe replace the word finite by countable. Maybe that would work. Okay, so by my tone of voice, you can tell that it's not going to work probably. And let's look at that. Let's look at exactly what happens in the next video.